Hello everybody and welcome back to ECMath. This is going to be another video on section 1.6, input transformations. I know there's already a lot of videos here, but I wanted to make just an updated video that kind of has the newest information and ways of explaining it. So let's, without further ado, let's get right into it. One thing I should add is that this should not be the first video you watch of mine about transformations. I'm assuming that you have already watched videos or been to class and you know the basic shapes of all the parent functions, and you understand each transformation, both input and output, individually when they're applied. This video is going to be more about what happens when you have a sequence of transformations, especially when you have a sequence of input transformations, because those are the most challenging ones. So let's get into our first example, which is not going to necessarily be about a sequence of input transformations, but it is a type of problem you might encounter, and understanding this is going to help when we do those sequences of transformations. So we're going to assume that f of x contains some given point. This time it's going to be 410. We don't know anything else about f of x. F of x could be, this could be f of x. And it could even be a piecewise function for all we know. But we do know that it has the point, this is not to scale, that has some particular point, and that's the only thing we know about it. We'll call that random point, point p. And we want to know, if we apply a transformation to this mysterious f of x, what will happen to point p? What will be the transformation, and sometimes that's called the image when you're talking transformationally, of point p under a set of certain sets of transformations. The first set we're going to look at is the transformation 1/2 f of x plus 4. And what's important about this is that when you chunk these out, these are both examples of output transformations. 1/2 is multiplied to the f of x, and the plus 4 is added to the f of x. So these are both going to affect the y coordinate. So I could imagine that I have the point P with coordinate 4, 10. Then I might do 1/2 of the 10 value, right? Because 1/2 does not affect the x value. The point P has kind of coordinates x comma f of x. So I'm doing 1/2 f of x is going to turn this into 5. And then we'll do 1/2 f of x plus 4 is going to turn 5 into 9. And so the way that we could find the image of that transformation on the y values, or the outputs, is by just plugging in the y value 10 into f of x, right? That's all it says is plug in y, which is really f of x, in for f of x. And we get the output is 9. So the transformation image of point P with this transformation would be the x was unchanged, but the y became 9 when we did 1/2 and then plus 4. Now let's go to step B, which would be doing an input transformation. These are a little trickier, or maybe not trickier, but they are different. So we might ask, what is the transformation or image of the point P within this transformation f of negative 2x plus 6? So all I know is that P is equal to 4 comma 10 still. That's the only thing I know. And this is kind of like x comma f of x. Now in this case, negative 2x and plus 6 are both affecting x before the function is applied. So these are input transformations. They're going to affect x, not y. So in this case, the y is actually going to be unchanged, and the answer already is I know it's just going to have a 10 there. If we think about what f of x really is then, it basically is like an in-out table where the only thing we know is 4 and 10. But if instead of having x here, I have negative 2x plus 6, I'm basically trying to work backwards in the table to figure out what x would actually be. So here's how you do it. I need to know what will make this equal to 4. So that I can apply f of x and understand that one point. So what I'm going to do is set negative 2x plus 6 equal to the x value that I am looking to transform. And then I'm going to work backwards, solve. There's a couple ways to solve this, but the most logical way is first to write it without parentheses. Let's take away 6. And then we'll divide by -2. And we would get that x is 1. I'm going to check this. Let's see. So if I plug in 1, I would be doing f of -2 times 1 plus 6. That would be the same as f of -2 plus 6. That's the same as f of 4. And I know one thing about f of x, which is that f of 4 is equal to 10. So what this is saying is that under this transformation, if x is equal to 4, then y would equal 10. And so the image of that point P under this transformation is going to be 4. Oh, nope. If x was equal to 1, y was equal to 10. Because when I plug in 1, I get f of 4, and f of 4 is 10. So the image under the transformation is going to be 1, 10. But what's really important here is the method that was used. The method that was used to solve backwards for an input transformation was setting that argument, the input, equal to the value that I wanted to know, and then working backwards, back solving. And what's important about the back solving is that I used opposite operations while back solving. To get rid of addition, I subtracted. To get rid of multiplication, I divided. This is actually the explanation for why all of the input transformations work in that backwards way, that a shift to the plus 6 in your equation is actually a shift to the left, for example, is because when you are back solving, you end up doing opposite inverse operations. So part C of this problem is just a combination of parts A and B. I might say, what's the transformation of point P, which again was 4, 10, with the combined transformation of a bunch of input transformations, -2x plus 6, and then 1/2 of x, f of x plus 4. Again, the input transformations are just going to affect x, and the output transformations are just going to affect y. So this is just a combination of the two previous answers. And I already knew that the x transformation gave me 1, and the y transformation gave me 9. So when you're doing something like this, you can, if you have this as the problem you're given, you can break it into what's affecting the x coordinate, for which you solve backwards, and what's affecting the y coordinate, for which you just plugged in 10 and solved, I guess, quote unquote, forwards. And that is how we could solve something like this. So if you were asked, what is the transformation of a specific point? Work with the x's by back solving, work with the y's by forward solving, and it's not really that bad once you know what to do. Example 2 is going to be really similar to this. So we have a function, and it appears to be some kind of absolute value equation, and that's fine, but we don't need to know the equation of the existing graph. Here's the graph of G, and the question is, where will the vertex be under a certain transformation? So, first, all I really need to look at is not the whole graph. I don't need to think about what sequence of transformations is happening. I just need to observe that the vertex is 2, 1. That is, I have the relationship that G of 2 gives me 1. Or that it contains the point, if x equals 2, y equals 1, if that helps. Now, I'm going to look at the x transformations and the y transformations. And I don't actually need the graph anymore. So this is just in G. I'll kind of box this out for the original. Let's do the x transformations first. So the x transformations would be -x minus 3. I need -x minus 3 to equal 2, the x value that was the x value of the vertex. So then I can solve this backwards. Let's solve it backwards by adding 3. So I get negative x equals 5, and then I'll divide by negative 1, and get x is equal to negative 5. That's going to be the x-coordinate of the new vertex. That is, it will be some combination of shiftage and reflectage, and it's going to end up at negative 5. Okay. Next, let's do the y-coordinates. So the y-coordinates are looking at the transformations negative 2g, blah, 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 plus 1. So now I'm going to take, I know that g of 2 is equal to 1, so I'm going to do negative 2 times g of x plus 1. That's going to be negative 2 times 1 plus 1, which is negative 2 plus 1, or negative 1. That's going to be, I guess I should write like y equals. So that's going to tell me the new y-coordinate. So the new vertex, which I arrived by solving backwards for x and plugging in the y value for y, is going to be negative 5, comma, negative 1. And just to prove this fact for you, I'm going to use a neat feature of Desmos, which is that if you type in a particular equation, so this is the equation for g of x, negative 2, absolute value of x minus 2 plus 1. It's just a vertex shift over and up and then a reflection downwards. But once I've defined g of x, I can do further transformations on it just by typing them in. So this is what we were solving, negative 2g of negative x minus 3 plus 1. Let's see where it is. All right, I have to turn it on. Oh, I can see the graph is over here somewhere. Where will that be? Where will that vertex end up? Negative 5, negative 1. So compared to our already transformed original, by solving kind of backwards and forwards, backwards for the x and forwards for the y, I can find out what a transformation of a transformation will give you. So let's move on to example 3, and this is where this is going to start becoming really useful. We're going to use our ideas here to move a parent graph. So we're going to let h of x equal x cubed. That's going to be the parent graph. And the question when you have x cubed, and you always want to know if you're trying to graph it, is where will the inflection point move if we have all sorts of transformations on it? Remember what I mean by inflection point is that turning point right at 0, 0, where it switches from concave down to concave up. So the inflection point at 0, 0 in the parent. So I need to know, where does 0, 0 move to? So if x is going to equal 0, then I need to figure out what in this transformation will make the piece that I've just boxed equal to 0, so that I can cube that value to create the inflection point. So what you're going to do is to solve the x values, is I'm going to set 1/2 x minus 1, the argument, the thing that's inside the x cubed, right? So I can see right here is the big parentheses that shows me where the parent function is. I'm going to set that equal to 0 and solve. So I'll add 1 and get 1/2 x equals 1. I do plus 1, plus 1. And then I'm going to do times 2, and I'll get x equals 2. So that's going to tell me the x-coordinate of the inflection point. For the y-coordinate, I'm just going to look at the output transformations. The only output transformation is plus 1, so I'm going to do 0 plus 1 equals 1. So in this parent graph, the inflection point just by solving backwards, I know is going to be at the location 2, 1. And I could use this to start drawing a graph of this function. So I'll plot over here the point 2, 1. Now, I also recognize, because I've studied transformations, that this 1/2 is going to do some kind of stretching or shrinking action. And instead of trying to think really hard about what kind of stretch or shrink it's going to be, let's just apply the same method to another point. I know that in the parent function, right, because like if I know 2 points and I have the symmetry of x cubed, I'll be able to make this graph, because then I'll really have 3 points. I know that in the parent function, x cubed, right after the inflection point, it passes through 1, 1. So I'm going to do the same deal, figure out where 1, 1 is going to map to. So to do that, I can take the entire argument here That's the x part, and I'm going to set this equal to 1. 1/2 x minus 1 equals 1. This is, by the way, I know there's two 1s. This is the first one. I'm setting the x's equal. So I'll add 1. I'll have 1/2 x is equal to 2. I'll times by 2 times by 2. And I get x is going to equal 4. That is, I'm going to have some point with an x coordinate of 4. Then I'll do the y's. The y is just, I'm at y equals 1, and then I have a plus 1. So my new y is going to be y equals 2. So I'm going to have the point 1, 1 is going to be moved to 4, 2. We can now go put that on the graph. 1, 1 was moved over to 4, 2. So this is already preparing me to basically finish the graph. I know that if the inflection point is right here, then the graph must curve upwards like this. And because cubics are still kind of odd functions, they still maintain their symmetry even after you shift them. I can also infer that I'm going to go through this point right here. And the function should look something like that. And if you don't like my symmetry argument, then just plot a third point. You can use -1, -1. You can use 2, 8. Use any set of 3 points, and once you have about 3 points, you'll know what the shape of the graph is. I'm going to pop over to Desmos and confirm that we were correct. Here it is in the same window as before, just to prove it. We do go through that 0, 0. We do go through 4, 2. I don't have a selected point. And you can tell the inflection point is right here at 2, 1, as we predicted. So, having that ability to back solve specific points that you know from parent functions can be really powerful when you're graphing. If you would like to graph point by point, then this is probably a really good way to do it. That said, it can get tedious because you kind of have to do like a little bit of algebra for every single point that you want to solve. So it can help to try to think about these as a sequence of transformations instead, thinking about transforming the whole graph, kind of the big picture, whereas the points are kind of looking at each individual small picture. It can be nice to look at the big picture. But our idea about solving backwards actually is the key for this. So that's what the next example should be about. So this is a little technical, so I've written out ahead of time, and let's just kind of see what we've said. So you probably noticed in the last example, which was 1/2 x minus 1, parentheses cubed, plus 1, the plus 1 doesn't really matter, that the shift was not actually 1 unit to the right, as you might expect from just looking at the equation, but actually a total shift of 2 units to the right. And it's sort of a mystery. Why does that happen? Why didn't this move over 1 and then up 1 and then get stretched around the point 1, 1? Why wasn't the graph going through 1, 1? Instead, why was it going through the point 2, 1? And the answer is everything what we did when we solved that equation. We set 1/2 x minus 1 equal to 0, and we did 2 operations. We first added 1 to both sides. Then we multiplied by 2 to both sides. The order that I solved that equation in is also the order that the transformations must occur in. So if I'm thinking about this as a sequence of multiple transformations, to get the correct end result, I would first have to shift 1 unit to the right, then do a horizontal stretch, which doubles all the x values, and then only in the end would I go do that up 1 shift, which again doesn't really matter here. Let me carry out those transformations over on the side here. Ooh, there. So we're going to carry out those transformations on x cubed and see if I arrive at the same graph that I just showed you on Desmos and we graphed earlier by plotting points. I'm going to graph this one not by plotting points, but by thinking about the sequence of transformations. I'll start by plotting the parent function x cubed, as well as including its inflection point and the points 1 to the left and 1 to the right of it. Then I'm going to take those points and shift them to the right 1 unit. 1 unit to the right. Everything would move over like this. And we would have a graph. Something like this. That would be step 1. I'll do a little index up here. That's step 1. Then I'm going to do the horizontal stretch. But remember what happens with a horizontal stretch. Mathematically, when you do this stretch, you're going to double all the x values. You're not just pulling it from both sides. You're pulling it basically from the y-axis. The only point that will not stretch is points where x is equal to 0. Every other point is going to have its x value doubled, which means that the point 1, 0 is going to move to 2, 0. And the point 1, 2 is going to move it's going to move to 4, 1, and I'm going to fix the coordinate. The point 2, 1 will move to the coordinate 4, 1. The y coordinates here are not yet changing. So, and then negative 1, 0 will not stretch. So now I've carried out the stretch, but notice what happened. The stretch actually stretched and moved the inflection point. So the stretching, because it happens second, has that power to move the inflection point, and that's why the inflection point happens at 2, not 1. Then we'll finally do the final graph by moving everything up 1 unit. That one's easy to do. That's how I get the 0, 0. I'm back. I hit 2, 1 again, but now it's the inflection point. And the final graph would look like something like that, which matches what happens when we typed in the actual equation into the function. So, if you're comfortable with this method, you can probably stop the video right here. Just remember that when you're doing transformations on input functions and you're thinking about them as a sequence of transformations, the order that they should be done in is first do your horizontal shifts and then do your reflections and stretches. But when you do those reflections and stretches, always remember that you're not reflecting over the vertex of the transformed graph. You're reflecting and stretching based on the 0 value, based on 0. So really think about coordinate points, not just kind of like shapes moving in space, but really thinking about coordinates. If you can do that, do these shifts in that order, you'll be good to go. So here's another example of the same thing. I have a square root function. I can tell that I have a double input transformation. So my first, and no output transformations. That's probably for the rest of the video. We're gonna ease up on the output transformations because the real challenge here is understanding what's going on with those input transformations, the x's and y's, because they operate strangely. Or the x's only, not the y's, because they operate strangely. So, what transformations occur and in which order for the graph y equals root negative x plus 4? First step, step 1. Step 0. Think about your parent graph. The parent graph has some really important points. It looks like this, but the most important point is 0, 0. It's not really the vertex, but it's like the vertex. So the most important thing to figure out is what x value is going to make everything underneath the root equal to 0, because that's where this graph is going to start. So I'm going to set the inputs equal to 0. And that will look like this. Negative x plus 4 equals 0. Then, step 2, I'm going to solve and watch the order. So, negative x plus 4 equals 0. Can't write that small. Let's zoom in. Negative x plus 4 equals 0. My first thing to do is going to be subtracting 4 from both sides. And that subtracting 4 is going to correspond with a shift 4 units to the left. Just like we'd see that plus 4, right? But we're actually subtracting 4 from the x value. That's what's going to cause that shift. Then, so then I would get negative x equals negative 4. To solve this, I'm going to multiply or divide by, I'm going to think about multiplying. I'm going to multiply by negative 1 on both sides. And so then I will get x equals 4. But what did that multiplying by negative 1 do? That was going to be, that's the thing that reflected over the y-axis. So the two transformations that happen in order are a shift to the left 4 units and then a total reflection over the y-axis. Why does it matter that those happen in this order? Well, let's look at what happens when we graph the result. I'll do 3 good points on the parent graph. So that's root x. Then I'm going to shift it over 4 units, 1, 2, 3, 4, and redraw the parent graph with the same relationship, so it would then look like this. Currently, this graph is at the point -4, 0. But now, I'm going to reflect over the y-axis. When I reflect over the y-axis becomes the line of mirror symmetry. And so where does -4, 0 go to? It's going to go to 4, 0. Where does -3, 1 go to? It's going to reflect over to, I should plot the point, 3, 1. And so on. The only point that won't change was the point 0, 2 of that orange graph. So here's what the actual, it's easier to draw it this way. That's what the actual graph of square root -x plus 4 should look like. Here's another confirmation. This feels really suspicious, right? That flip really doesn't seem okay, especially at the start. Here's a confirmation though. When you solve that equation, look at the result you got. We said that x needs to equal 4, which would mean that 0, 0 should be mapped to 4, 0. And look at where it ended up. Not the vertex, but that starting point really did map over to 4, 0. And just to prove it for you, here's that equation in Desmos. It really does have its vertex at 4, 0, not -4, 0. And this is deceptive, right? Because you might think, if you were initially looking at it, you might think that the shift is going to be 4 units to the right, because plus, no, that's a lie. You might think that the shift is going to be 4 units to the left, and then the reflection would kind of just change the direction. Or you might be tempted to do the reflection first, and so the graph that people often end up with is this graph here, and that would be wrong. You have the right direction, you have the right size of the shift, but it's ending up in the wrong quadrant. And that's because you have to be really careful when you complete that secondary reflection. This might be a good point in the video for you to actually stop and go do a couple practice problems and make sure that you're really, really confident in doing transformations, sequence of input transformations in this way. But say that you're not going to pause. I'm going to show you another shortcut, a way that I actually find easier, but some students find harder because it's going to involve changing the equation and thus changing the order of transformations. So it is more algebraically complicated, but it makes your graphing life easier. And we're going to do the same problem in a second way. So this is the same graph. We're going to have the same result, but I want to show you a cool trick. Let me rewrite this as y equals the square root of negative parentheses x minus 4. So what I'm doing here is I'm factoring off all negatives and coefficients. Factoring off all the negatives and all the coefficients from the equation. In this case, there were no coefficients, but there was a negative. The -1 technically is the coefficient. Then, to solve the x, I would still set, like step 1, I would set negative parentheses x minus 4 equal to 0 and solve. But keep track really carefully of the order that I solve this in. But to solve this, now the negative's on the outside. So as I solve from the outside in, I would first multiply by -1. And that's going to correlate with the reflection over y. That's step 1. And then I would get x minus 4 is equal to negative 0. Oh, but negative 0 is just 0. So then to solve this further, I would add 4, which is going to correspond with a shift 4 units to the right. So notice how I have the opposite order. In this case, I'm reflecting first, and then I'm shifting 4 units, but I'm shifting 4 units to the right because the act of factoring this changed the sign on the inside. So it changed the direction of the shift. I think this is a lot easier to graph now. What would this look like? So if I were to graph these transformations in this order, here would be the parent graph. I do the reflection, but I don't have to think about what the line of symmetry is. It's just a lot easier to create that mirroring right here. And then I can just take all those points. So in this case, the mirror line was right on the vertex. Take all those points and move them over 4 units, 1, 2, 3, 4. And arrive at the same result. So when you're doing those input transformations, if you would like to do the reflection first, which may be easier when you're drawing these, if you're going to do that reflection first, you have to make sure you factor out the inside and factor off any and all coefficients and or negatives. That would also permit you to do the stretch first, too. So the order of the transformations that you're going to do is always the order when you set the argument here equal to 0, you're going to solve that equation in a specific order. And the order you solve that equation is going to be the order of the transformations that you approach on the graph. And then we still get, by the way, x equals 4 for the solution of that equation, which tells you that the vertex should happen at x equals 4. So I already know where the vertex is. I'm just looking at the direction of the graph in kind of a different way. So because all this might be confusing, we're going to do one more example of it. We're going to do the same transformation using both of those methods. The first method that we'll do is the order as written. So the transformation, or the equation we're looking at, is going to be y equals absolute value of negative 2x minus 6. And there are 3 transformations going on here, right? So if I look at it, I have a reflection, I have a shrink, and I have a shift. That's a triple input transformation. That's a lot of stuff going on. So the order of those 3 things is really, really going to be important. And it's going to be helpful to figure out the right order. Where will the vertex go? The general approach for this first one is, as always, set the argument here, everything inside the absolute value, that's a terrible bracket, I'm sorry, equal to 0. So we'll say 0 equals negative 2x minus 6. And then I'm going to solve that equation out, making careful note of the steps I take. So the first step I take is going to be adding 6 to both sides. That's going to correspond with a shift by 6 units to the right. So then I would get 6 equals negative 2x. Now I'm going to divide by negative 2. Divide by negative 2. That is going to correspond with a horizontal shrink and a horizontal reflection. Those 2 can happen in the same order, right? Because I'm dividing by negative 2, they are kind of the same priority, and it won't matter the order that we do those in. So I just did whatever I saw first. And then I end up with negative 3 equal to x. Negative 3 equals to x is also going to be the new vertex, or at least the x coordinate of the vertex of this parabola. And since there's no y transformations, no shifting up or down, I know that that's where the actual vertex is going to be, is at -3, 0. So let's carry this out then. And look at how can a shift of 6 land me with a vertex of -3? Well, it's going to matter based on exactly where that reflection, or the shrink and reflection take us. So this is an absolute value graph. We're going to need more space for problem 2, huh? Okay, so I have absolute value graph. It looks like a V. Make as much room here as I can. I'm going to shift this 6 units to the right. 1, 2, 3, 4, 5, 6. And draw this out. I'm going to plot like a good number of points here. The more points you have when you're doing something like a shrink, the happier it's going to be. Okay. Then I said I'm going to do this, compute this horizontal shrink. Oh, so this is step 1. Compute this horizontal shrink. So to do the horizontal shrink, you take all of your x components, you take all of your x components and divide them by 2. We're dividing all the x components by 2. So 6 is going to go back down to 3. 4 is going to go back down to, did I count right? 6, 5, 4 is going to go back down to 2. Oh yeah. 4 is going to go back down to 2. 8 is going to go back down to 4. And not only did we make the parabola, or the absolute value graph, skinnier, whoa, that's not a good line, skinnier by doing this shrinkage, we also moved the vertex. You can imagine that this is like a spring. It's like a spring attached to 0, which is the only point that isn't going to move. And if you then push the spring in, every point of that spring is going to compress, including the vertex. Sorry, I'm trying to clean up my graph here. Okay. Now I have this graph, and I have to do a horizontal reflection of it. So that's going to take all x values and make them their opposites. So 3 is going to go to -3. 2 is going to go to -2. 4 is going to go to -4. And the final graph then will look like, or should look like, this. That would be the approach if I was doing the transformations in the order as they were written. And I can double check then that my final vertex really did happen at x equals -3, which is what I got when I solved the equation at the very start. So that's your check, right? If your vertex ends up in the right spot, then you're going to be, you know this is basically going to work out right. Now let's approach this by factoring that inside value and see if that can make our life easier to graph, right? Before we had to shift, I didn't put my order on. Then we had to stretch, then we had to reflect. And it just made things kind of difficult. So let's try this factoring the inside. You do have to be a little comfortable with factoring here. So we'll say y equals the absolute value of -2 parentheses x plus 3. So you're pulling out that common factor. Then I'm going to still do the same move. I'll take the argument here and set this equal to 0. So -2 parentheses x plus 3 equals 0. And I'm going to solve it keeping track of my steps. The first step, though, is going to be to divide out by -2. That's going to do the horizontal shrink and the reflection over the y-axis. And then the result is x plus 3 equals still 0. So notice how easy that is. To solve this, we'll subtract 3, we still get x is equal to -3. And that subtracting 3 corresponded with the shift by 3 units to the left. Now I want to graph this based on this order that I just determined. So I'm going to use this order to sketch a graph. I think I can fit it over here on the side. All right, parent graph would look like so. Then the first thing I could do is the horizontal shrink. 0 doesn't shrink. I don't have to worry about the vertex moving here because the vertex is still at 0 at the time I do the shrink. That's to me the big benefit of this, is I don't have to worry about the vertex moving. Similarly, when I do this reflection over y, so that was step 1. When I do the reflection over y, my graph is still symmetric across y-axis. So the reflection over y is just the same thing, no change. Now, if your graph was like a cubic or something, you would still do a reflection here. It's just in this case, nothing happened. I did the reflection and it mirrored itself. So I have this skinny v, and then the final step is just taking my skinny v and moving it over 3 units. And sketching that final result. So to me, that's a lot easier, factoring out that inside, than trying to figure out, oh, where does the vertex move through all these sequences? But you do have to be okay factoring out the inside. And always remember, always, probably the most important thing you can do with these is set that argument equal to 0, because that's going to be your check. If you set the argument equal to 0 and solve, that tells you where your vertex will be. Always. Always going to work. And that works with pretty much every function. If it has an identifiable vertex, or like sine of x has a particular behavior at 0, 0. If you can set that to equal 0, solve it around, you'll figure out where your graph should be kind of starting. Okay, this has been kind of a long video. I'm going to close it out with a summary. So, to find transformations of output points, y values, you just plug it in. You apply the operations that you see in order to the y coordinates. That was like the very first example. We didn't do a lot of y coordinates in this video. On the other hand, to find transformations of input values, you're going to take the input value that was given to you as being on function and setting it equal to whatever you see inside the argument. And that works with 0, but it works with any other number as well, like when we transform 1, 1 on the cubic. If you have a function, you want to know where the vertex or inflection point or just any other important thing is going to move, you can set that input equal to 0. Setting the input equal to 0 is like the best strategy you can do with these complicated transformations. It can help you do the transformation. It can also just be a really good check. Finally, if you're doing horizontal stretches and reflections, notice that stretches and reflections still always happen with respect to the y-axis and or 0 point, even if you have a vertex that's way over here. So if you have a vertex that's over here, but you're shrinking it down, the vertex is going to have to move as well. Which is why we talked about maybe ways that you can change the order of your stretches so that you're doing all of those difficult stretches and reflections first. And that's the last point, which is that the way you express the equation can affect the order you do the transformations in. And there are multiple ways to approach it. I would recommend picking a way to do this that works for you. Most of the time, those triple input transformations are not going to show up. But when they do, it really helps to be prepared and to have a plan and just know what you're going to do ahead of time. So pick a method that works for you, practice it a couple times, and then you'll be ready whenever you see these strange things. Also, we didn't do a lot of y transformations here, shifts up and down and vertical stretches and reflections. Do your input transformations first, get that, and then the y transformations work as normal. Those are familiar to you, so they're not going to be anything really messing you up in the middle of a problem. All right, folks, thank you for watching. It's been fun. Please let me know what questions you have. I realize that this can be a really tricky topic. It's graphical, it's algebraic, it's got a lot going on, so please send me your questions. Thank you all for watching. Have a nice day.